talk about an application to representations of affine algebras and barely mention W algebras, and hopefully in the last 10 minutes I can mention something about W algebras. We'll see. So, the starting point for all this comes from, as for many things, from Beilinson-Bernstein localization. And so let me recall this. So let's say B is a Lie algebra, B is the Borel. And I can look at G mod B. And this is defined to be B modules with a B action such that two little B actions coincide. So this appeared in several talks this morning. This is very close to what we call category O for G. And if you're interested in character formulas for this, the way that we deduce character formulas for this, the Cauchy-Lucian conjectures, is through this equivalence due to Beilinson-Bernstein. That G mod is equivalent to, G mod 0 is equivalent to D modules on G mod B, where D mod 0 means principal block, or I take the Harsh-Chandra center of the universal enveloping algebra, and I set the character to be the W dot orbit of 0. Have I said anything wrong so far? Good. And so from this, it follows that if I'm interested in category O, you get a similar equivalence, and you get B equivariant B modules on G mod B. And then you can use all the theory, all the algebraic geometry we know, to do some properties about composition multiplicities here, and that gives you the composition multiplicities in category O. But also I'd like to note that the Beilinson-Bernstein theorem, it applies not just to this category of B integral representations, but actually to all representations of G. And that's going to be relevant later. Okay, so now let's talk about the affine case. So in the affine case, so let's look at, is this visible for everyone? Great. Take the affine Lie algebra G hat. Inside it, it has this central part, C times 1. And I can look at representations. I can fix a level, kappa, and so this just determines how C times 1 acts. Now you can split the representation theory of G hat, splits into 3 cases. There's positive level, which I'm going to write as kappa is greater than kappa, and I mean I need to say what this actually means, but I'm just not going to worry about that. It's going to be greater than half the killing form, negative, which is the same thing but less than, and then critical level is the same thing but it equals to. What's up?
It's greater than negative.
Yes, sorry. And the rest of this talk is going to focus on the critical level case, but let me just note that these 2 cases, we understand category O. By also a Beilinson-Bernstein localization theorem. call localization theorems because you need to do the positive and negative case separately. Due to Kashiwari Tanizaki, and I think I'm also getting some other names.
Yeah, a priori is not clear about the zero level as you explained there, right?
What's zero level here? Or
Yes, here it is clear, but here, you, what would be G mod 0?
what is? Oh, you're referring to yes, this will come up.
Yeah.
Don't worry. So so this will seg into the next statement, which is what is the statement of Beilinson-Bernstein of, let's say, affine Beilinson-Bernstein at critical level. So the statement you want is going to look something like, well, as an example statement, which is not true, if you look at just the affine category of all modules, you could hope that this is equivalent to D modules on the affine Grassmannian or D modules on the affine flag variety or whatever. And the statement is horribly false, but this is the form of the statement we want. So why is this false? The first reason has to do with what you mentioned, the central character here. So a fact is if kappa is not the critical level, the center of the universal enveloping algebra is trivial. It's just the identity. On the other hand, if kappa is the critical level, forgot to write a center here. On the other hand, if kappa is a critical level, the center is actually very big. It's this polynomial ring on infinitely many variables. I'm going to write this as functions on the space of operators, which I'll define soon. And interestingly, we get operators for a langlands duals group, and this is the first incarnation of langlands duality inside this theory. And as a cursory link to W algebras, this is the W algebra for G at critical level, and operators are the W algebra for the langlands dual group at infinite level. So this is an example of Fagan-Franken duality for operators. And I should state, this is due to Fagan-Frankel. Before I forget, let me define what operators are. Operators, I'm just going to do this for G, are going to be equal to ET plus F plus B of T. So this is the E. You're taking connections of this term, mod, and N of T gauge action. You're taking a specific form of connection, mod, gauge transformations. But the gauge transformations had to live in that. So this is an affine analog.
So you mind us who F is?
Oh, sorry. So here, I'm using similar notation as Gerbier. So E is a Borel, and F is a principal nilpotent, and here I'm taking F inside N minus. So as an example, think for G equals SLN, and think of F equals the matrix, which, I mean, it's usually something other than 1, but also it doesn't really matter. So just think of the matrix that's all 1s below the diagonal. And you can compare this with a finite type statement, which is that if you take not f but loops into b, but just take f plus b, and you quotient out by n. First off, the first part of this is that the n action is free. And the quotient is a nice simple algebra. It actually turns out to be the spec of the Harsh-Chandra center, which is also the spec of the principle, of the finite principle W algebra. So this is just an affine analog of that, and an affine analog where we added this connection aspect. So this gauge action isn't just conjugation.
Sorry, in your definition of OPG, what is before the first plus? What is it?
D. So this is D for derivative.
Okay. Thank you.
Yeah. So there's some more geometric description of this in terms of G connections, but I'm not worrying about that. Here's simple explicit form. So just like here, f plus b mod n, spec of the Harsh-Chandra algebra, this is just some affine space. In this case, one fact is that off G is an infinite dimensional affine space. It's infinite in the same way Laurent series is, so it's infinite in both like the power series direction and the negative direction. And inside this we have off G reg, which is the same thing, but where instead of Laurent series, I take power series. And this is also dimensional affine space. But here it's infinite dimensional in only the same way as power series. Okay, any questions so far?
So OBGREC is an actual scheme and OBG is an
Yes. This is a scheme. This is an in scheme. Alternatively, can't remember the words correctly, but like this is actually the vacuum module for the vertex algebra, and this is like the algebra of all operators. Okay. Where did the eraser go? Oh, it's right there. Any questions so far? So, the first obstacle, let's start by trying to write down the affine Beilinson-Bernstein statement. So classically, the Beilinson-Bernstein functor is given by global sections. Similarly, I can take D modules on the affine Grassmannian, where as shorthand, the affine Grassmannian here will be the in scheme loops into G, mod arcs into G. I can take D modules on the affine Grassmannian. I also have a global sections functor, and it lands in modules for G hat. So the first reason this can't be an equivalence is that, well, for any f, the action of the center, which is O of hop, LG, on global sections of F, factors through O of hop, LG brag.
Gmod. It's actually should be like Gmod critical.
Yes. In general, everything I'm going to say for now on, unless I explicitly say otherwise, is going to be for critical level. I'll try and write it, but if I forget, assume I mean critical level. So here, actually I also mean crit, but you can twist it away, so whatever. Okay, so for any FD action of op LG factors through op LG reg, this should make some sense because remember I was saying that this is some op G is an infinite dimensional scheme in both senses, or it's an infinite dimensional in scheme in both directions. While if I take, say, the vacuum module here, this is infinite dimensional in only one direction. So by taking global sections here, I can't possibly see the entire center. I can only see this restricted part. So that means, first off, that the functor from d crit of Ger, if I take global sections, it'll land in this category, g hat mod, still have to write a crit reg, where the center factors through this. And if I want some statement like Beilinson-Bernstein, well, there's no op LG reg action here. So if I want a Beilinson-Bernstein statement, I have to factor further and add a character here. So the point is, even with this reg, this side has an op LG reg structure. Every module for g hat here is also a module for functions on op LG reg, or is also a sheaf on op LG reg. And there's no structure like that here. There's also a structure over here that isn't on the right-hand side, namely on this category acts the geometric Satake category, which is d crit g of O. Let me get a longer piece of chalk. Double cosets for the arc group. And geometric Satake tells you that this thing is equivalent to the category of representations for the Langlands dual group. However, if you've never seen this, don't worry about this. We won't use this too much. But
what kind of categories do we consider? Do we consider derived categories?
So far I'm considering only abelian categories. But, I mean, you're correct that in the end, everything is secretly derived, but the equivalence is going to be abelian. I mean, the way we would argue is we prove the derived equivalence and then we show that it's t-exact. So right now I'm cheating and talking about abelian categories, but to actually do anything, I'm going to need to switch to derived categories. Yeah, and maybe I should just switch to derived categories immediately. It'll make the next step a little easier.
So the convolution with objects in the Satake category is t-exact. Is this a statement or not?
Oh yeah, yes. Actually, yes, that's true. Yeah, that's fine. Yes, that's a statement that implicitly I'm making, but right now I'm still doing motivation. But yes, implicitly everything is okay, even rigorously, because this action is t-exact. So let's unify these two pieces of structure. Let's say a category over X, where X is like some kind of, I'll say, geometric space. I guess I'll just say, I can say stack here and it covers both these examples. I can take stack X is a category with an action of the category of quasi-coherent sheaves on X. Again, I want to do this derivatively, but for now I can still get away with not doing it derivatively. So let's see how both of these have the structure. Well, if I take quasi-co on point mod G here, or point mod LG, this is rep LG. And so d crit over Ger is a category over, or for shorthand, lives over point mod LG. And on the right-hand side, what do I mean by op LG reg structure? Well, for any g hat crit crit reg module M, and any module over its center N, I can take M tensor N, and this has a g hat module structure and is still in this. Sorry, I should just write tensor over the center. And so here I'm using that Z as central, and so you can tensor over Z and still get a g hat action. Okay, so you have this statement, and because we have this tensor action, g hat mod crit reg. Oh, I'm supposed to write this on the right-hand side. Lives over op LG. And the moral of the main theorem is basically that the fact that these two spaces, that these two categories live over different geometric spaces is the only obstacle to Beilinson-Bernstein. Namely, for any map x to y, there is a pullback operation sending a category C over Y to a category which I'll write as C cross sub Y, X over X. And the main theorem
concretely just tensoring up. Yeah.
It's tensoring up. It's tensoring up. Is that if I take g hat mod crit reg, this is isomorphic to D of here, where I just base change from point mod LG to op LG reg. Any questions on the statement?
Can you just spell out why there's a map between?
Yeah. There's a map between op LG reg to point mod LG. So what is this map? Well, this map is just saying there's a canonical LG torus on op LG reg. And remember, op LG reg came as some kind of moduli space of connections. Moduli space of connections on the formal disk. So if you just take the fiber at 0, that gives you a canonical LG torus over every kind of op LG reg. And this works in families, and this gives you a map like this. Any questions? Okay, so this is the statement of the main theorem. Let me say some history. So this was the first written instance I know of this. Where does this conjecture is? This was conjectured by Franco and Gatesgory. I don't know if it's possible they learned this somewhere else, but that's where it's written down. So, and right away I'm going to say that they had a series of 6 very long papers, and these 6 very long papers, they prove every possible statement about this if you restrict to category O. So in other words, if you only care about category O, nothing else in the rest of my talk accomplishes anything. So from a point of view of character formulas for category O, this was completely solved by Franco and Gansgary. Sam Raskin proved this for rank 1 groups. I'm just going to write G equals SL2 here. And then this is due to Sam and I in general. And again, I wrote this as a statement for abelian categories. Really, we proved the derived version of this, and there are some derived subtleties there that I'm just going to completely ignore for this talk. Any questions so far?
Again, what was this LG torsor on the?
Yeah. So this thing is actually I can probably just write this better as evaluation. This was D plus F plus dt. This was this quotient. Because this is power series, you can evaluate at t equals 0. So if you set t equals 0, this maps to it maps to f plus b mod n, and this maps to point mod g. It's possible that what I wrote is literally incorrect, but at least like this is more like what's happening.
F plus B mod n is this AK you're saying, this spec.
AK. Yeah, that's a good point. What I'm writing down is literally incorrect.
Yeah.
Will you accept the answer that it's plugging in t equals 0?
Wait a minute. The quotient still admits a map to point mod G. Because n sits inside of G, and you just map the.
Yeah, it does, but this doesn't actually map to f plus b mod n because the gauge action doesn't work out that way.
Right.
But okay, so maybe let me translate this a little more correctly. This is some space of connections mod gauge transformations. It's a space of connections on the disk, so in particular it's a space of bundles on the disk. For each of those bundles, you can take the fiber at the origin, and that gives you a G-torsor at that point. And a map to point mod G is specifying a G-torsor above every point of this. Morally, this map is evaluation at t equals 0, but evidently I need to think a bit more to actually justify why this map is okay with the gauge action.
Maybe you say it's the map, just you forget the connection.
Uh,
Kind of, I don't know. Yep.
Yeah, that sounds right.
Confusing because it seemed like you were trivializing here when you wrote it this way.
Yeah.
I mean, a map to point mod LG is a principal LG bundle.
Yeah.
The principal LG bundle is take the fiber at the origin.
Yeah. I will note, if you don't care about any extra symmetries of this, like, this might as well be the map that factors through point. There are no non-trivial G-torsors on an affine space. The only reason that, like, you write down this specific map and you try and make it, and you try and define this in the canonical way is because you might care about the symmetries coming from automorphisms of the disk. But if you don't care about that, you just say, take this map to point mod G.
Oh, okay.
I mean, if you want to globalize this at all, you need to care about automorphisms of the disk, but honestly, I don't really care about globalizing anything, so this is good enough for me. Okay? So I'm going to talk about some ideas of this proof. And so this talk is technically about this result, but it's also could be subtitled Locogeometric Langlands is useful and you can use it too. And this is how we'll prove this theorem. So the idea here is that we're going to understand these two categories as categorical representations of a Looper group. So let me say explicitly what this means. You have a monoidal category D modules on a loop group. This is some in scheme, so there's some infinite dimensional technicalities for defining this, but morally this is like somehow not really that much more complicated than D mod of G, and it has a monoidal structure from convolution.
So it's the basic question: does D crit just mean untwisted D modules? Or?
D crit, so crit is a integral twist. So I haven't been paying too much attention to it because if you want, you can just untwist everything.
Okay, so is it D crit here or?
Yeah, it should be D crit here. You're right. I will definitely drop some more crit subspaces, so feel free to stop me if you see anything. So you have this monoidal category D mod G of K, and a categorical representation of G of K is a category with an action of D of G of K. So morally, one way of thinking about this is this some categorical version of the group algebra. If you're familiar with the representations of p-adic groups, this is actually a more properly categorical version of the Hecke of the big Hecke algebra, and the definition is actually rigged to basically mirror that. But a representation of a group is a vector space with an action of the group algebra. A categorical representation of a group is going to be a category with an action of D modules on the group. And the point is that both of these categories are going to be categorical representations of G of K. In the case of D of Gur, this is pretty clear. You have an action of D of G of K on D of Gur by convolution, just because you have an action because, well, G of K acts on Gur itself. So this is a categorification of the fact that the space of functions has a G action if the space itself has a G action. D of Gur has a G, so D of Gur has a G action. It's a little less obvious, but you can check that the point mod LG action commutes with this G action, and so actually this right-hand side has a D of G of K action. Why does the left-hand side have a G of K action? Well, if you take, I'm going to work fine dimensionally to illustrate this point. If you take G mod, this is G modules on G that are weakly equivariant on the right. Weakly, just write G weak. Because, well, the universal enveloping algebra sits as this thing inside D, and tensoring up, it gives you exactly the weakly equivariant, the right weakly equivariant D modules on G. But you still have the left action, and that gives you an action of D. So D mod of G acts on this by convolution from the left, and that commutes with the right G action, so anything will still be weakly equivariant on the right. And basically the same thing will hold for the affine Lie algebra. So if you believe this, and you believe that this has an affine analog, then that explains where the G of K action on both sides comes from. So let me outline now Sam's proof of this for G equals SL2. And Sam's proof of this for G equals SL2 really makes a lot of use of this G of K action. So proof of theorem for G equals SL2. If you take, so you can define a map from the D of Gerside. D of Ger across point mod LG, op LG reg. There's a version which is basically modifying the global sections functor to work with this fiber product from this to G hat mod trip reg. There's this functor. You can show that global sections of mod is fully faithful. In fact, it turns out that this is formal, but non-formally, the way you show it is that it boils down to, well, it turns out that manipulating this a bit, you only need to check this for the vacuum module, basically, and so this is the computation of endomorphisms of the vacuum. Once you've shown that global sections mod is fully faithful, it suffices to show that the Serre quotient C is 0. And here's where some inspiration from number theory kicks in. So, yes?
Quotient of the entire category by the image.
Yes. So here's where some inspiration from the representation theory of p-adic groups kicks in. So, as I mentioned earlier, these definitions of G of K representations on categories and so on and so forth, they're motivated by similar considerations in p-adic group representation theory. And a theorem is that for a representation of SL2 of QP, if V is non-zero, either V has a Whittaker model or V has Ewahorian variance. I should write this in a straight line.
Drooping down, yeah.
Yeah, I am. It's a bad habit of mine. Apologies.
You can lift the board up a little, you know.
That's a good idea. I've never thought of that. Either V has a Whittaker model or V has Ewahori invariance. So V having Ewahori invariance is a statement that Vi equals 0. So either Vi is not 0 or wit of V, which I can write like this, isn't 0. So what does this mean? This is, well, what's invariance? It's Hom from modules over that group of the trivial module to V. I should write this in a category module agnostic way. It's homomorphisms from the trivial module, or if we're doing categorical representation theory, the trivial category. You take these homomorphisms, and that gets denoted by Vi, and you may note that this is compatible with some of my earlier notation. So earlier I wrote G mod B for category O, or not category O, but B integral modules. And that's because you can compute that this is exactly B invariance on G mod. So either Vi isn't 0, or it has invariance for a more complicated group. Namely, you take the loop group of the maximal nilpotent and you impose a generic character on it.
QP, now you're, p-adics.
What's up?
QP, now using the p-adics here.
Yeah, so that's the original scope of the theorem. So this is a motivational theorem. This is what motivated Sam.
Jack, I have to give you an N of QP.
Yeah, because n round t now. It's like
Sorry. Yes.
You put covariance too, right?
Yes, but I'm gonna avoid worrying about that. Yeah, so in number theory, you want to talk about this as a functional on V. For us, the difference between invariance and covariance is less big, so I'm not going to worry about it. But properly speaking, this should be co-invariant.
It's the theorem for any representation.
This is the theorem for any representation of SL2QP. So a way of saying this is that the induced representation from Iwahori and the induced representation of Whittaker generate the entire category. And so to figure out if any modulo is 0, you just take a hum from one of those two. And now what Sam proved, same thing for representations of the loop group. For categorical representations of the loop group. Either they are going to have Iwahori invariant, or you're going to have Whittaker invariant.
For SL2.
For SL2.
And it's the original theorem, I guess, is also hold if you use the Laurent series.
Yes. Yeah, the QP versus Laurent series distinction, they're like sort of, for most matters, it doesn't end up affecting all of these sorts of theorems very much. So how do you prove this localization theorem that C equals SL2? Well, we wanted to show that C equals 0, so we show that Ci equals 0 and that Whittaker invariance on C is also 0. So Ci equals 0. This follows because Franco-Gates-Gray proved the original conjecture on category O. So we still use that as an input. There are ways to reduce how much of that you need, but the simplest way is just to directly use that. The second statement, so this is equivalent to showing that the original map, this is equivalent to showing that you have this isomorphism between D modules on Gur and of K chi cross point mod G check off G check reg, that this is isomorphic to Whittaker invariance for the same thing for G hat mod crit reg. And Sam proved also that if you take G hat mod,
Do you need like an abstract isomorphism of module categories, or do you need it to be given by this modified global?
it's given by this modified thing, yeah. But this is not so hard to check. If you take G hat mod, Sam proved that if you just take G hat mod crit and you take Whittaker invariance itself, this gives you representations of the W algebra. And the critical level W algebra, as previously discussed, is just op LG mod. So when we impose this reg condition, this becomes a quasi-co of op LG reg. This becomes quasi-co of op LG reg, because this what this category is known, and you have this theorem. Any questions about that? So phrased in this way, so now let me make some statements about the proof for general G. Phrased in this way, one idea for proving the statement for general G is idea. Find a set of generators for for the category of G of k categories. So before we said every category, if you want to find out it's 0, you can apply Whittaker, and you can apply Iwahori for G goes SL2 specifically. So in general, we're going to find a set of generators for G of k cat for any G. And again, we take inspiration from number theory. So in number theory, Moin Prasad show that every representation has an invariant for one of their subgroup character pairs. And I'm not going.
Sorry, now you're explaining the proof of the statement that always either you have Iwahori invariant or.
No. That proof is done. That proof is the Iwahori case was Franco-Gates-Gorey, and the Whittaker case is you apply the theorem of Sam and just calculate both sides explicitly.
I mean, I thought you were explaining this theorem of Sam now. No.
Oh, so this was the SL2 case. Right. Now I'm explaining the general G case. So that's why I wrote for any G. You're trying to find a set of generators of this for any G to replace the role of Whittaker and Iwahori.
Oh, I see. Okay.
Does that make sense? Cool. Yeah. So Moin Prasad basically in number theory gives you the analogness in number theory. I'm going to phrase this a little differently now than from the generator way. So we phrased. So we define a canonical filtration on any G of k category C. And it's going to be a Q-index filtration. Not all rational numbers are going to appear. The denominators are going to be bounded. So importantly, you're going to have a discrete set. But there's going to be a canonical filtration on any G of k category C. So that means, i.e., a sequence of subcategories C less than or equal to R inside C. And so this generation statement is that for each R, we produce a category. Oh, let me write. We produce some group character pairs K of x comma R chi such that the supported in degree R part is detected by this. Such that if C less than R is not the same as C less than or equal to R, then C K of x comma R chi is non-zero for some x.
So k x comma R is some subgroup,
Yes.
which is compact, non-compact.
It's a compact subgroup. As one example, if x for some values of x, and if R is an integer, this is the nth congruent subgroup. So that's one example of this, but more of these in general are a little harder to describe, which is why I'm not defining it here.
So for L2, you can exchange, the idea is that you can somehow exchange n of k by some compact subgroup, which may be even
Yeah, so that's part of this.
or something like that.
Yes, yes. So Iwahori is another example. All the things in the commutator series of Iwahori are examples, actually. So those are some examples of these subgroups, but the general definition will take some time, so I'm not writing it. And then the idea is that we calculate this filtration on G hat mod. In particular, you have a slope filtration on top G, and so let's say op G less than or equal to R is in op G less than or R is offers with slope less is the slope less than R part. This is also an affine state. It's very explicit. It's just saying I say some Fourier modes are 0, and that's the only condition on this. And G hat mod, G hat crit mod, the less than or equal to R part is exactly G hat mod op G less than R. And we proved that using this theorem.
G check.
Yeah.
Do I understand that, for example, module in category O can have module in category O has very strong restrictions on what its central character can be?
Yes. Yes.
Statement of this kind?
Yes. Yes. Category O is going to have extremely strong restrictions. It's only slope 0. So that's the other part of this. Op G reg is inside op G less than or equal to 0. So this theorem shows that we only have to worry about so this is called depth. We only have to worry about the depth 0 part. And to finish off the proof, and if I take the category of the loop group mod the unipotent radical of Iwahori, this generates the depth 0 part. This generates depth 0 G of K representations. So the structure of the proof is we had these two sides. First, we show that they only have depth 0, that everything is detected by this less than or equal to 0 part. And we show that using this generation statement. And the depth 0 part is quite relatively simple because everything in there has I0 invariance, where I0 is radical of Iwahori. And that statement is the category O statement that was proven by Franco Gates-Gory again. Any questions on any of that? Okay. So let me, in the last 5 minutes, let me say something. Let me say some slightly irresponsible things. So what does this give you for W algebras? So let me start with a remark. So the same thing, this gives you a filtration on W mod, and W mod less than or equal to R can be explicitly described
So is W still over the critical level?
No. This is a good point. W is not necessarily over the critical level anymore. This gives you a filtration on W mod, and W mod less than or R can be explicitly described as W modules where certain Fourier modes vanish. If you want to know which specific ones, they're in a paper of Gerbier with Sam. It's quite easy to write down, but it's kind of hard to describe purely in words without setting up notation, which is the only reason why I'm not saying it, but it's something extremely natural. So this is just this is just coming from the Moy-Prasad thing. For VSORL, you just take the standard generators and you say they vanish up to after some point. So this is something that can be described kind of naturally, but at the same time, this theory so far doesn't tell you that much about these categories, because actually it turns out that if you want to prove, so if you want to do geometric langlands, this filtration is sort of not enough. So there is a more refined filtration which is indexed by what I call columns, which are increasing functions. And this comes from number theory again, because why not? Increasing functions from q greater than or equal to 0 union a minus sign, which just represents any negative number, going to mapping to twisted levies in G viewed as an algebraic group over Laurent series. And here's, so claim geometric langlands. So geometric langlands, local geometric langlands, is a classification of G of categories with a loop group action. These can be very complicated. My claim is that all of that complexity comes from extension classes between different columns. So claim GL is okay if you split by column type. And W algebras as something coming from G hat mod, which you can study via geometric langlands methods, you can analyze with this. So you get this filtration of W mod, as you're going to see. And I will write this as a suggestion because, I mean, I haven't checked all the details and this is very far from written. So really what I want, by the way, is I think the statement should be easy from a pure W algebra perspective, and I want someone who actually knows something about W algebras to tell me how to prove it. Because the way the logic in this subject usually works is you prove something about W algebras and you use that to prove geometric langlands. And so this is like sort of a perverse way of doing this. So W mod, if you take the subquotient of this filtration, the subquotient can be written as D modules on an open set in an affine, tensor quasi-co on a specific torus. I'm going to write Z0 because it's going to be the center of f of 0 when it's connected. Quasi-co of Z0 of the complexified character lattice minus Z0 mod Z0. So this looks complicated, but like it's kind of simple. Tensor the category O for W of the twisted levy given by f of minus. And so what this is saying is that up to these choices of things, which are just data for giving a character, the subquotients of W mod can be written W mod, even if you consider arbitrary big modules, the big modules can be broken into pieces, and the pieces can be understood as category O, W algebra category O for a twisted levy. And I'm over time, so yeah.